Okay, so for question 11, we have a BJT in a common emitter amplifier configuration, emitter bypassed. We have some values here for the for the circuit. We know first that the input resistance is 20K. It should be 2K. Okay, so this one here, this version that I'm using, it's incorrect, so it should be just 2K. Then beta is equals to 80. Rs is equals to 1K, R1 equals 20K, and R2 equals to 100K, RC equals to 2K, RL equals 1K, and then the early voltage 100 volts. So first we have to draw the small signal equivalent circuit. So remember that for that, the capacitors, they become a short circuit right here and there. And then VCC here, it's also grounded, right? And then if we use the hybrid pi model, we have, so for part A, we have the voltage source Vs here, small signal. We have Rs here. Then we have R1, R2. Here's the base. Then we have the small signal model itself, the hybrid pi. So the emitter again, it's short circuited because of this capacitor here, CE, so it's grounded. Then we have the current source here. Now we have our out again, right? Then we have RC and RL. This is basically our collector. This is our out, RC, RL. And then here we have, this one here. Then here we have GM times VBE. VBE is this one here. Sometimes we refer this one here to as the input voltage. And then here we have our pi. Now, for B, compute the small signal parameters. So we have to calculate part B. We have to calculate the small signal parameters. So first thing here is that we know that R1, so let me just go back there. So we have the values for R1, 20K, and R2, 100K. So we know that this parallel here, so we call R12, right, is equals to R1 in parallel with R2, and that's equals to 20 times 100 divided by 120. Okay, so K here, that's 16.67 K ohm. Now we know from the statement of the problem that the input resistance Ri, which is R pi times R12 divided by R12 plus R pi, right? We know the value of Ri, we can determine R pi. So in this case, if we isolate R pi, it's equals to minus R1, R2, Ri, R12 divided by Ri minus R12. And this gives us 2.27 K ohm. So this is the first term that we have defined for the small signal model. So to calculate the transconductance GM, we need to know the collector current. So we can determine IB as VT divided by R pi, and that's 11 microamperes, right? Then we can calculate IC using the beta, right? So this gives us 0.88 milliamperes. And now that we know the collector current, we can calculate the transconductance. So the transconductance is IC over the thermal voltage, and in this case is 0.0352 amperes per volt. Okay, so we got those here. We also have our pi here. We are just left with the output resistance, small signal resistance. So our out is just the early voltage divided by the collector current, and that's equals to 100 divided by 0.88 milliamperes, right, volts here. So this is 113.63 kilo ohm. So that's the third parameter. Okay. Now for part C, we have to determine. So let me go up there. So we need to find our out and the overall voltage gain AV. Okay. So the output resistance, we know that it's going to be just RC in parallel with our out. And this gives us 1.9654 kilo ohms. And then for the AV, we know that's AV1 times AV2, which is pretty similar to question 10, right? So we have AV1 equals to RI divided by RI plus RS, which is 0.667. And then AV2, which is equals to minus GM times R out in parallel with RL in parallel with RC. And this is minus 23.33 volt per volt. So the overall voltage gain is just AV1 times AV2, which is minus 15.55 volt per volt. Okay, so that's it for this problem.